Hello and good morning, everyone. This is our Senior Project 1 second progress presentation. We are supervised by Drs. Mohamed Shalan and Tamer ElBatt. I am S Basta, here with my colleagues Farah Seif, Lobna A ElHawary, Maram H Abbas, and Mariem H Elzayadi. And our idea is the Intelligent Monitoring System for Precision Agriculture. This is our table of contents. We'll recap our idea and our timeline goals. We'll go through CARE's requirements and their greenhouse. We'll go through our system architecture, followed by the section talking about the server in our database, our progress and our analysis, and finally, the plan for our next presentation. Here, I'll be going through the recap of our project idea. To remind you all of our thesis, we are proposing an intelligent agriculture monitoring system for Cucumber Greenhouse in the Center for Applied Research on the Environment and Sustainability, also known as CARES, that uses Internet of Things and machine learning. The Internet of Things portion is for the remote sensing network that uploads the sensor readings to the cloud. The machine learning portion is to detect the plant's growth stages and any NPK deficiency that might be affecting the plant. NPK here stands for nitrogen, potassium, and phosphorus, and they are the three most prevailing types of deficiencies that could affect plants. Images from the cameras are uploaded to the cloud to train the model and to feed into the model. An interactive web application for the users to monitor sensor readings and to be notified when any of the values are outside the ideal specified ranges that the user would enter. The project outcome here is community deployment, and it will be deployed at CARES. Now Farah will be going through the recap of the timeline goals.
So for our timeline, we are actually on track as we have gathered all of CARES' requirements, purchased our tools, and finished laying out our IoT system. The only thing we have not yet started is the data collection phase for the project, as CARES still did not begin their experiment. But they informed us that it will begin on December 22nd, so we expect to start then. Now, what exactly are CARES' requirements? We have summed up their needs into four things: a remote sensing network that measures pH, soil moisture, temperature, and humidity per block, an application, a web application to view these readings and interact with our system, and a machine learning component that will help us detect the two critical growth stages of the cucumbers, as well as detecting nitrogen, potassium, and phosphorus deficiencies in the plants. And we will work on this next semester. Now, to show you the greenhouse layout, Maram will proceed.
So as you can see here, this is one side of the actual greenhouse that we're going to be testing our project on. Now this diagram is to aid in showing how the full greenhouse looks like. It is divided into 16 different rows, and each row has 5 sections. Each row, as you can see, measures to be 17 meters long and has like about 55 pots each. So this is how CARES are planning on dividing the greenhouse for their coming project. They will be having 3 experiments, and each experiment will have like 4 rows of their own, as you can see here. I would also like to clarify that our project is not only used to cater this way of division and is actually more flexible. However, we only wanted to show you how will the place that we will test our project on will look like. Now I will leave you with Samer, who will be discussing a proposed system architecture.
So to start us off with the system architecture, I'll be going through Wi-Fi or BLE. Although BLE has half the power consumption of Wi-Fi, in the next few slides I'll be explaining why we actually ended up picking Wi-Fi. Taking the layout that Maram mentioned earlier, each row is 17 meters. The Raspberry Pi will be stationed right into the center of the greenhouse, and that is at least 2 meters away from any row. Taking this into account, that means that if a sensor block is at the end of the row, that means it could be 19 meters away from a Raspberry Pi. With that in mind, also keeping in mind, according to Bluetooth's official website with an official calculator that you can plug in different parameters, transmission rate, Bluetooth protocol, the type of setting that you're in, the maximum estimated range turned out to be 13 to 17 meters, which means using Bluetooth would actually end up limiting our implementation. We still need to implement this realistically on our own and come up with our own results, but for now we're sticking with Wi-Fi.
So this is what we settled upon on our system architecture. So as you can see here, Each sensor's block will be connected to one ESP32. Each sensor's block has three main types of sensors, and first is the DH11, which measures temperature and humidity. And second, we have the pH sensor, and third is the soil moisture sensor. So we will be having the Raspberry Pi, as you can see here, connected through Wi-Fi with the ESP32 and with the camera in which it gets data from both of them, and finally it will upload to the cloud here periodically. And as you can see here, we have like n number of sensors blocks, which is connected to be like also n numbers of ESP32s, since each sensors block is connected to one ESP32. And we have like m number of cameras. So this architecture is like variable to any number of sensor blocks or cameras needed for the project. So in this slide, we're trying to show how we're trying to show you like how will the sensors be connected to the ESP32. And as you can see here, the soil moisture sensor is connected through the analog pin over here, and in order like to work. However, the pH sensor and the DHT11 need only like digital pins normally. And another main thing here is that the soil moisture and the DHT11 can operate through the 3.3 volts in the ESP32, but the pH sensor needs 5 volts to work, so it uses an external power source. Now I will be leaving you with Mariem to discuss how our system links to the server.
So now we'll explain why we chose Google Cloud over Amazon Cloud. Even though Google Cloud has less APIs than Amazon Cloud, it still fulfills the requirements for our system and offers all the APIs needed. Also, it offers a free trial of 90 days and $300. But the main reason we chose Google Cloud is because it offers command line tutorials, not only console or website or GUI-based tutorials. And we need those command line tutorials because most of our system depends on automatic scripting. Thus, terminal or shell work is more appropriate for us. And this is why we chose Google Cloud. So now we'll present the APIs for Google Cloud that we use. So the first is IoT Core, which reads from connected sensors and integrates those readings into software. Another is PubSub, which pushes requests to an online service, and that means a remotely hosted code. Another API is Cloud Run, and that's the main agent in our system. And it is the API that runs the code in the form of Docker images. Another API is Cloud Storage, which stores files in buckets. Another is Cloud Vision, which detects image features, which we're going to be using for the MPK deficiency and growth stage detection. Finally, Cloud SQL, which of course stores structured data. And because the version of Cloud Run that we are using, called Cloud Run for Anthos, is less secure than the ideal version, which is called Cloud Run Fully Managed, we decided to take some manual security measures to make up for that security loss. The first is making the cluster, the collection of servers that we are implementing our service on, private. And that means that the cluster will not access resources from public networks, which might compromise its own security. We also made the cluster internal, which means that the opposite, which is that the public networks, the public clients, will not be able to access the cluster because its IP is now private. And the cluster's IP is basically the IP of its load balancer, the entity that balances processing among the servers of the cluster. So for the time being, until our GUI and our machine learning model is complete, we deployed a sample service. However, the required service would go as follows. It would report the readings that are on SQL to the GUI, and also it will analyze the images on cloud storage in the form of the machine learning model that we implement, and then reports the findings to the GUI. And it's also worthy to note that the SQL uploading and the storage uploading is done by the Raspberry Pi, as mentioned before.
So for our database, we're going to be using Google Cloud MySQL. And this is an entity relationship diagram of how our database is going to be. So we have 5 entities: user, user access, project, and sensors and image. And the relationship between the user and the project is through user access, and it's a many-to-many relationship. For the project and the sensors, this is the sensor readings table. So one project has many sensors, and similarly, one project has many images. And the project here includes all the project settings.
Now we will move on to the web application portion of our presentation. This is the use case diagram for our web application. As you can see, we have a user. This user can sign up and create new credentials. Once these credentials are formed, the user can use them to log in. And every time the user tries...
Just a second, I think there's a problem in the video. I'm gonna so I'm so sorry, just a second.
Now we will move on to the web application portion of our presentation. This is the use case diagram for our web application. As you can see, we have a user. This user can sign up and create new credentials. Once these credentials are formed, the user can use them to log in. And every time the user tries to log in, the username and password are verified. If they are incorrect, then an error message will be displayed. Once the user is logged in, they can create a project or edit a project, or they can view sensor data. This sensor data is retrieved from Google Cloud Run. The user can also choose to download this data or view it in graphical form. The admin user is a type of user that can use all the other functionalities a normal user can use, in addition to generating a security token. This security token is used when a user is signing up in order to verify that this user signing up is actually part of an organization and they should have access to the system. This is the sequence diagram for the scenario where the user tries to create a new project. We have 4 objects, as you can see: the user, the application, Cloud Run, and Cloud SQL. First, the user requests to create a new project and inserts the settings of this project. Then the application sends a request to Cloud Run to create this project with the following settings. Then Cloud Run sends a request to Cloud SQL to add this project to the project entity. Next, Cloud SQL sends back an acknowledgement to Cloud Run. Then Cloud Run shows the project on the application front end. And finally, a success message is sent to the user. Now we will show you the prototype of our web application by starting off with the home page, where the user can learn more about us and our system, and they can log in using their email and their password. But first, they need to make an account and sign up. In order to sign up, a user needs to have a security token, as we mentioned before. This security token has to be provided by an admin and is a means to verify that this user is actually a part of this organization and can have an account. Once this user has an account, they can now log in and view all the projects that they already have, and they can add new projects. They have to enter these parameters in order to make a new project. There are some values that can be taken as a default if the user does not enter an input. Let us take as an example what the ideal temperature ranges does. If the sensor reading of the temperature sensor is outside of these ranges, then a notification will be sent to the user. Now, the user can also change the block design. This makes our system flexible and not just catered to CARES. Now let us look at the project Cucumber that this user has made. This is the block design that this user has made. Now let us see the sensor readings of block A by clicking on it. These are the sensor readings that were taken at 3:40 p.m. The user can then generate the line graphs for these data. Now, the user can also download the data and can choose the start date and end date of the data that they want to download and the information that they want downloaded. They can download this as a CSV. The user can always change the settings of the project as they like.
So now I'm Maram and I'll be talking about remote sensing architecture. Okay, so the sequence diagram simply shows how do we get readings or data from the sensors. So first of all, the Raspberry Pi sends a request to the ESP to get data over here, and the ESP32 reads from the sensors and returns it to the Raspberry Pi, and then it uploads it to the cloud SQL so that the cloud run could get the latest read data from it. So I'm going to show you right now how the Raspberry Pi is going to read data from the ESP32. So we have this Python file which is going to run on the Raspberry Pi, and what actually this Python file does is that it asks for the data, it sends a request, and then it reads the data when it replies back. So if I run this Python code, it simply will print data 22, which means that the data it read is actually 22. So what happens in this Python file is that it reads temperature. As you can see here also, if I went through the IP address or the server of the ESP32 on the temperature page, it's going to still print 22. So it reads the temperature of 22 degrees Celsius and it simply prints it, which is the same thing as what happens in the Python code. Now I will be leaving you with Farah.
So this is a sequence diagram showing the interactions between the Raspberry Pi, camera, cloud storage, and cloud run. The Raspberry Pi requests an image from the camera, and the image is returned back. And then it uploads this image to cloud storage, and the cloud storage sends back a message that it has been inserted. And whenever Cloud Run requires any images from storage, it gets them, it gets the latest images, and storage returns them. So this is the camera model we're using. It's EasyViz C6CN, and we access the streaming of the camera using network streaming by the camera's IP address. So this is a screenshot of what it looks like, and this is the IP address of the camera. Next, we're going to be discussing some analyses that we have done for the project. The first is power analysis for the ESP32 board, and we're investigating two power modes, modem sleep mode and deep sleep mode. So the modem sleep mode power consumption is 25 milliamperes, and the Wi-Fi active mode power consumption is 180 to 240 milliamperes. And we're looking at readings every 10 minutes. And we decided to keep the active period for the ESP in this mode, in this analysis at 5 seconds, and the rest of the time it will be spent in the sleep mode. This resulted in an average power consumption of almost 27 milliamperes and the battery lifetime of 4 days for a 2500 milliampere battery capacity. The next mode is deep sleep mode. So we're doing the same thing, but instead of putting the ESP in modem sleep mode, we're putting it in deep sleep mode for 9.5 minutes out of the 10, and it's going to be active for 30 seconds. And the power consumption for this is a lot less. It's 150 microamperes. So this graph shows the trend of the battery lifetime versus percentage of deep sleep time. So now we were faced with a huge question, which is how are we going to power our system? The battery that we have just investigated in deep sleep mode resulted in a lifetime of almost 9 days. So we decided to investigate a battery with a bigger capacity, and this made the lifetime increase up to almost a month. And then we thought, what if we increase it even more? So we decided to opt for a power bank, and the lifetime was more than 2 months, which was really great, at a cost of 390 pounds, a one-time cost instead of the recurring costs for the batteries. But the problem with this is that we're going to have to disrupt our system for one entire day and not take any measurements because the power banks are going to be charging. Another option is using a power plug. And this is not going to cost us anything, and it's going to be able to supply power to the system forever, as long as electricity exists. And this is the layout of the greenhouse as shown earlier. So we thought of putting the wires of the power plugs either running under the blocks or hanging from the ceilings. And we've actually discussed this with CARES, and they are on board with it.
So in order to check the robustness of our system, we performed some traffic analysis. So we wanted to calculate the transmission time for all the readings and then for each image. So because we have 48 readings and they are all very small quantities, each reading would have one unit or one frame. In this case, it's a Wi-Fi frame. Thus, the frame sent would be 48 frames. And we calculated the transmission time by assuming the maximum transmission unit instead of the actual transmission unit per frame, and over the data rate, which is 100 kilobytes per second, which is the minimum data rate that we plan to implement on CARES grounds. And that gives 0.135 seconds for the 48 readings. As for the image, because it will be fragmented into multiple units or frames, we multiplied those frames by the same calculation, and this led to 4.9 seconds. And this shows that the system, given the data rate that we plan to implement, is relatively robust. Also, another benefit of this analysis is that it served the power analysis that was explained by Farah previously, because here we just wanted to make sure in the power analysis that the on time that we assumed would be equal or larger than the transmission time needed. And now Tamer will explain the storage analysis.
And now the storage analysis. For the sensor readings, we are taking 4 float data type sensor readings per 10 minutes per ESP. So in a day, that's 144 10-minute periods times 4, because there are 4 sensors, per ESP, which is N, times 4 bytes, because it's a float. That equates to 2.25 N kilobytes per day. Now for the camera. Per camera, we are taking an image each day. An image is 1080p JPEG format, 500 kilobytes. So that means in a day, we're taking 500 times M kilobytes per day. That equates to, as a total, 2.25 N plus 500 M kilobytes per day. Assuming that the amount of ESPs are 12 and the amount of cameras are 8, that is currently around 6 megabytes per day. That is more than enough days on SQL, because taking into account that the SQL with the free service is around 31 gigabytes. And now the problems in our current solution. The camera and the ESP32 are unable to connect to the AUC WLAN. This is because AUC's Wi-Fi is an enterprise connection, and that means since they're not running full operating systems, they just can't connect to the Wi-Fi. We've tried contacting the AUC IT department, and they said they couldn't help us. So we have thought of two other solutions. We've thought of having the Raspberry Pi, while running Ubuntu, to run a Wi-Fi bridge, since it can't connect to the AUC Wi-Fi. And this has worked, but we still have yet to test how far the connection goes. And our second solution is to get a USB modem, but this still requires further testing. Secondly, we have insufficient funds. So as we mentioned earlier, we can only get 5,000 from the department. There is the application in January, but we're still not sure if we can get this, and we are just accumulating cost. And for the last section in our presentation, our plans for the next semester. Firstly, since we've successfully tested out the camera, now we just need to purchase the rest of them and start installing them in the CARES greenhouse, especially now that we're getting very close to the start date of their experiment, which is supposedly December 22nd. We want to also finalize the GUI of the web application and start integrating it with the pub and sub upload service so that there's also functionality. Finally, we also need to start the portion of machine learning of our project. Thank you for listening, and please feel free to ask any questions now.